Good morning, everyone. So let's start by reviewing quiz 2. Quiz 2, like the first quiz, has 4 questions. The first question deals with these two mechanical systems, and the objective here is to find the differential equation describing the motion of each of these two systems. What is common between both of them is that they have two masses. In other words, they have two degrees of freedom. There are two motion variables that describe the status of this system. If you call x1 position of mass 1 and x2 position of mass 2, those are the degrees of freedom that I'm talking about. So what would be the order of these systems when it comes to model of these systems? Fourth order. So for both of them, you arrive at two second-order differential equations whenever you write a mechanical differential equation or an equation of motion for a mechanical system. It will end up being a second-order differential equation. Because we have two masses, they would be two second-order differential equations, therefore a total of fourth order. Now, if we were to choose one to discuss further, which one would you choose? Which one would you like for me to discuss more? Any? Or you're okay? I don't have to go over the solution if you're fine with it. Yes?
Could you just answer what was the input for B?
For B, that's a great question. So for B, there is no clear input. There is nothing that comes from outside that would cause motion. So that's where you have to choose based on the purpose of modeling. So potentially the input could be motion of one of the masses. Yeah, so it's your choice. And that was part of the question for you to realize that for input and output, many times you have a choice. It depends on your purpose of modeling. Anything else? Do you want me to go any further in any of you? It's your time, so I want to spend it in the direction that benefits you the most. So if you want me to draw the free body diagrams and write the equations because you face some difficulty, let me know. And even if you don't say anything now and you change your mind throughout the solution for the quiz, let me know and I'll do it gladly. I just don't want to repeat something that is clear to you. Going once, twice, you're okay with the first equation, everybody? Yes? Okay. So I'm not going to draw the free body diagram, but essentially the way to solve first part of the quiz is to draw two free body diagrams for each of these problems. One for mass 1, one for mass 2. If you need to make assumptions about the relative magnitude of the displacement, you need to make those assumptions. And then find the direction of forces based on those assumptions and write Newton's second law. So these are the main steps. And then there is that rearrangement step that I talked to you about to make the second order differential equation as close as possible to a standard form so you can talk about similarities and differences between systems. Okay? Everybody okay? All right. So let's move to, so in a sense, we talked about question 2 as well. So I answered the question about input of the first problem. I said you have a choice. Displacement of mass 1 could be your input, and therefore displacement of mass 2 and the rest of state variables could be potential output, or the other way around. Mass 2 could be, its motion could be your input, and the other state variables could be potential outputs. Now the third question asked about finding the differential equation for this system, for this electrical system, between the input voltage and output charge. If you remember, so let's go ahead and write the differential equation for this system. So if you write Kirchhoff's law for this, so what do you have? You have V, this is a closed circuit, you have V minus I A R minus, what is the equation for the inductor? What do I need to write here for the inductor? So it's L di A over dt. And the last one is minus 1 over c integral of IA dt. And if you're, because you're adding the voltages around a closed circuit, that's equal to 0. That's an equation we got from the past. So it's already on the slides. If you need to refresh it, you can also go back. But that's essentially the equation. We are applying voltage law, Kirchhoff's voltage law. Now, what we did last time in order to turn this to a purely differential equation was what? What did we do afterwards? We wanted to get rid of the integral to only have differential equations. So what did we do? Would you like to take a shot at it? What did we do last? We differentiated it. Now what I'm offering or asking you to do is to use another technique. Take advantage of the fact that integral of current is electric charge. So Q is electric charge. So accumulation of current, like what happens on a capacitor, you're basically accumulating the charge coming through on the plates of a capacitor. That is called electric charge. So if you do that, then you can arrive at a differential equation without having to differentiate that equation one more time. And that is beneficial, as you would see in a second, that your input can remain voltage, not its time derivative. Because if you differentiate this equation, everything has to be differentiated, including the voltage. So you have to deal with derivative of voltage as your input. Now, if you go with this definition, where it says Q is integral of IA dt, so immediately the last term of the equation has a name. It would be Q. Integral of I dt would be Q. Now, what will happen to di over dt? What will di over dt turn into? Or I, for that matter, the second term of the equation. So if you look at this equation and differentiate it with respect to time, so if this becomes Q dot, in other words, what will become the right-hand side of the equation? If you differentiate the integral, it simply is I. So Q dot is IA. So we took care of the second term of the equation and last term of the equation. What is I dot? So what is di A over dt then? Absolutely. So it would be Q double dot. So what did we do? We introduced a new variable. We called integral of current our charge, and then every other term that involved I turned into some sort of function of Q. Now you can now rewrite this equation. So let me only take the I terms on the left side, and I'll push. So basically push the I term to one side, which would be the right side, and keep V on this side. So I'm going to go start with di over dt. So it would be L Q double dot. So we're taking two steps at the same time. We are also rearranging the equation. So that's Q double dot. Then we have plus R Q dot plus 1 over CQ is equal to V. It should be immediately clear that one of the benefits of this change of variable, because it is now very similar to M x double dot plus B x dot plus KX equals to an externally applied force. So you can see the effect of V is like the effect of force on a mechanical system. It causes everything to start moving. It causes the charge to start accumulating or flowing through. And you can see the similarity between a capacitor, and what element in mechanical system? Spring. So a capacitor so a charge accumulates. So in a sense, electrical energy accumulates in a capacitor that can later be released back to the circuit. Or the resistant acts like an energy dissipation element, like a friction element, like a damper element. And the damper element dissipates mechanical energy, basically takes energy out of the system, and that's exactly the same function as for the resistor. And also you can see the effect of inductance, L, and similarity with mass. So it's like an inertia element. So it slows down the ramping up of the current and the charge. So that's the benefit of making this change of variable. I think we hit both third and fourth part of the quiz. Anything before we move on? Yes.
For that second spring system up
Yeah.
there with that force F coming off of it,
Yes.
could we put that as the input?
Absolutely. Yeah.
Okay, so
Yeah.
the input could be that force or either of the masses. Is that correct?
Can you repeat that last part of the question one more time?
So when I asked you earlier about the first spring system, what the input would be, you said that depending on what you want to get out of your differential equation, you can either put the input as one of the either mass 1 or mass 2 or possibly both masses. So when you're looking at the second spring mass system, you have the force actually coming off of it. So could that be your input as well as either masses?
Oh, typically for the stage that we are. So the question was for the second mass spring damper system, when a force F is applied to M2, it is clear that this is what causes the system to start moving. So that's a clear choice of input. Once we choose that, I'm repeating the question. Once we choose that, should we also keep another displacement also as another input? The answer is no. At the stage we are looking at systems that have one input. There are systems that have multiple inputs, but we are limiting our conversation to systems with one input. So F would be the natural input, the natural choice for input for the second system, and any of the velocities and displacements, so there are 4 of them, 2 displacements, 2 velocities, could be any one of them or any combination of all of them would be your output. Okay? Other than that, any other question? Do you feel good about the rest of the quiz? Okay. So let's go backward and review what we did last time. If you recall, last time we started the conversation about another way of modeling called a transfer function. A transfer function is a ratio. By the way, transfer function is a model. The same way a differential equation is a model of a system, regardless of its physics, transfer function is also a model, and it's a ratio between the output in the numerator and input in the denominator when both of them are in Laplace domain. So we have the approach typically is that we already have the differential or differential integral equation of the system. We take that equation into Laplace domain and we strive to find a ratio between output at the top and input in the denominator, and that would be the transfer function. We also mentioned that the same way by looking at a first order differential equation, by looking at it, especially if it is rearranged into the standard form, we can, for example, talk about the time constant of the system. We can the same way talk about the time constant of the system from its transfer function. And for that to happen, we need to take the transfer function into this standard form where we have a constant times s plus 1 at the denominator. And that constant that is being multiplied by s is the time constant of the system. Anything else? Any questions about the approach so far? That was the review of what we did last time. Okay, so let's keep going. So this is an example in this electrical circuit that is made of a resistor and a capacitor. Our interest is in developing a model between the voltage 1 that is applied between the 2 terminals on the left and voltage 2 which is measured between the two terminals across the capacitor. So we want to know as we apply and change voltage 1, what will happen to voltage 2. So that's a circuit or a logic that we are making. So the very first step is to come up with the differential equation, which will later on transform and take into Laplace domain. So if you write Kirchhoff's law around this circuit, you get to this equation 1 here. So that's Kirchhoff's law. V1, because the others are negative, you push them to the other side. I r plus 1 over c integral of I. I r is voltage drop across the resistor. Integral 1 over c integral of I dt is voltage drop across the capacitor, and that closes the circuit. So the next step is to take this into Laplace domain, to take the first equation into Laplace domain, and you could immediately see that there is a mistake in this equation. What is that mistake? So how do we take that equation 1 into Laplace domain? We take it one element at a time. One element at a time. So let me write down here. Laplace transform. So Laplace transform of I, which is a function of time, times r, which is a constant, simply going to be r multiplied by what? Simply multiplied by I of s, because I is a function of time, but we don't know what function. We don't know if it is a constant, it's a ramp, it's a sinus, it could be anything. So we simply are going to say whatever I is, we are going to find its Laplace transform, but we don't know what I is. So for now we are going to write it only as I of s. We are simply saying we went to Laplace domain. We are no longer in time domain. That's what we are saying. So that's Laplace transform of the first one. Now, what is the Laplace transform of 1 over c integral of I of t dt? So let's start with 1 over c. What will happen to that? Is 1 over c a function of time? It's a constant, so we are simply going to write it again, the same way we wrote r again. So 1 over c is a constant, it just carries forward. Now we have an integral. What was Laplace transform of integral of a function? So you need to maybe go back a few pages or a couple of pages in your notes, if you're taking notes. If not, I can do that for you. I can roll back a few slides and show you the main properties of Laplace transform. We talked about Laplace transform of time derivative of functions, first and second, for to name two, and also Laplace transform at the bottom left side of this, Laplace transform of integral of function. So Laplace transform of integral of ft dt is fs, where fs is Laplace transform of ft divided by s. So an integral is equivalent to division by s. So what will happen then? So the integral is going to turn into 1 over s multiplied by I of s. 1 over c, which is the constant, the effect of integral, it will turn into 1 over s, I of s, which is now the Laplace transform of I of t. So we talked about two of the elements. What is going to be the Laplace transform of v1 of t? V is the input. It's a function of time, and we don't know what function of time. So it could be anything. So what is its Laplace transform? Would there be an s multiplication, s division? No, simply it will carry and becomes capital V 1 of s. And that's the mistake that I mentioned to you. So here it should be V1 of s, not V1 of t. When you take the Laplace transform. Okay, so we talked about the Kirchhoff law and took it to Laplace domain. Let's talk about what V2 is, because remember, we want a relationship between input V1 and output V2. So I need to bring V2 out. Now V2 is voltage across the capacitor, which is going to be equal to 1 over C integral of IT dt. So we can take this second equation also to Laplace domain. And if you do that, you get your V2 of t turns to V2 of s. That's the Laplace transform. And we already know Laplace transform of this portion would be 1 over Cs I of s. We have already transformed that. Okay, so a transfer function, so this is now a transfer function, is ratio of output, V2 is our output, divided by our input V1. And we determined that V2 was output, V1 was input from the outset. We knew that before coming to the modeling. Okay, so we know what V2S is. We are going to put it in the numerator. We also know what V1S is. We have already found it. So we put both of these into this ratio. And from it, so if you look closely, V2 is 1 over CS IS. But I'm not writing IS here in the numerator. The reason is V1S is also R plus 1 over CS times IS. So there is an IS in the numerator and IS in the denominator. They cancel each other, so they go away. So it's an algebraic manipulation. You can do that. So then you can further simplify that. You can make you can make CS from the denominator the common denominator, so you can cancel it with CS from the top. So it becomes 1 over RCS plus 1. And you can see that RC is the time constant. RC, R times C, is the time constant of this system. So if you want to make this system faster, you have two choices. What are the two choices? How can you make this system faster? So faster means what? Faster means the time constant should go down. That's the meaning of faster. So how can you make it happen? Either the resistance should be smaller or the capacitance. So by making either of the two smaller, you can make the system faster. So that can happen if R or C, either one, go down. So by making them smaller, you can make this system faster. So this is a first order system. This is a first order system. We already found the time constant of it simply by looking at the transfer function. Okay, we talked about the time constant. I want to bring to your attention another property of first order transfer functions. So when you have a first order transfer function like this one, like what you have here, and we are underlining, this is the transfer function that we found for our system. Now we are adding another element to the standard first order transfer function when we have the standard denominator. The standard denominator is plus 1. Always remember, the plus 1 should be there. So if there is a constant times s plus 1, nothing else, plus 1, then what is sitting in the numerator now has a meaning and has a name. We call it k. For the example that we solved, k is obviously equal to 1. But k has a meaning and a significance. K is called the DC gain. So k has a name. It's right here in this busy text. So DC gain. DC gain means what is the steady state value of output? What is the steady state value of output for 1 unit of input? So DC gain basically tells you the value of output for every unit of a constant input. So that's the meaning of the steady state gain. So in other words, if you apply 1 volt to this system, if you apply 1 volt to this system, I want you to go ahead and plot the response with important values highlighted on it. So highlight the time constant, highlight the value at the time constant, and highlight the steady state value of the response. So what is the steady state value of the response? So in other words, if V1 is like that, 1. So it comes on at time 0, you flip a switch, you apply constant voltage of 1 volt to the left 2 terminals, and you attach a voltmeter to the other side where you measure V2, what are you going to record? If you plot those data points, what will you see? So what type of response will it be? You already know that. This is a first order system, so we know the type of response. We'll start from initial condition, which is 0, at time 0, and gradually goes up, and we'll find a steady state value. And now we know what that steady state value is because we know the DC gain. The DC gain of this system is 1, which tells you for every unit of input, that is the value of output. So the steady state value of the response, therefore, is equal to 1. It is equal to 1. Okay, so you know that this will settle at 1. So if you wait long enough, it will go to 1, which is the steady state value of response. But how fast will it go? You know that it will take RC, which is the time constant, to get to 0.63. So it takes RC seconds to get to 0.63. So this is the value here would be 0.63. 63% of 1 would be 0.63. So at this, so we'll pass through this point to go to the steady state. So the plot would be, so the response would look like. So it didn't quite pass through it the way I plotted, but you get the idea. So at this point, the value of response is 0.63, and it's an exponential rise, and it settles at 1 as the value of a steady state response. So see, simply by having the model, you gain a lot of insight about the response of this system. Now, if the voltage, if V1 is 2, if you apply 2 volts to it, what will happen to the response? It simply will amplify. The exact same shape, but the steady state response would be 2. Why? Because this is a linear system. So if you double the input, the output simply will double. Okay? So quick question for you. If you double the input, what would be the value of output at time equals RC? So if V1 is 2 volts, what is V2? What is V2 at RC seconds?
1.26.
How did you calculate that? You took 0.63 and multiplied by a steady state value of V2. So V2 steady state, which we know is 2, so it's going to be 0.63 3 multiplied by 2. So 1.26, right? 1.26. Okay, before we go to this system, I want to go back a couple of slides and show you another system. What I have at the bottom of this slide are two seemingly different form of differential equations which are essentially the same. So you immediately recognize this equation, equation number 1, don't you? This one. What is this equation? This is equation for what? For a mass damper spring system with an input of force. So it's a mass damper spring system with an input of force. You can immediately recognize that. What is the second equation? Hint, you probably spent a few classes on it when you were taking the course vibration of mechanical system. So what is zeta? What is omega n in that equation? Which one is natural frequency? Omega n, and zeta is damping ratio. So you take the first equation, you divide it by m, and you call portions of it appropriate names, so you arrive at this form. So you call, for example, k over m as omega n squared. See that? Can you see that? If you call k over m as omega n squared, you arrive at this form. And because we are dividing by m, the force now becomes force per unit mass. That's something to always remember. When you take the equation from form 1 into the second form, the right-hand side is no longer of a force. It's force per unit mass. We need to always remember that. So if someone asks you, take equation 1 into Laplace domain and form a transfer function between input force and output displacement, you would say, okay, I can do this very quickly, and I let you do it first very quickly. So take equation 1 into Laplace domain and form transfer function between input f of t, which appears f of s when it's in Laplace domain, f of s, and output f of s, and output x of s. Please go ahead and find this transfer function and repeat this from equation 2. So use either of equation 1 or equation 2 to find this transfer function. So please take a minute and find this before I show you the response. And we are going to put that right here after this slide. So what is this? How do you solve the problem? You need, I think we all agree that we need to take this differential equation to what domain? This is time domain. We need to go to Laplace domain. So we need to transform this entire equation into Laplace domain, which means what? Which means each of these four elements, mx double dot, bx dot, kx, and f, we need to transform them one by one into the Laplace domain and rewrite this equation. The equation will still be the same, it just transforms to Laplace. Okay, let's do it one at a time, and I need your help. So if I transfer this into Laplace, what will happen? Look at your notes if you have to. I want you to answer this question. So m would m be there simply because it's a constant. So m would simply be repeated. X double dot turns to what? It will turn out to s to power 2 multiplied by x of s, right? That is the Laplace transform of x double dot if, please remember that, if all initial conditions are equal to 0. If not, there would be two more terms. If you look at your notes, you would see that in general, the Laplace transform of x double dot has two more terms that involve initial conditions, initial position and initial velocity. But because we make that assumption that initial conditions are equal to 0, we can simply write Laplace transform of x double dot as s squared times x of s. Okay, so let's now go to this item plus what will happen to bx dot? So why don't you take a shot at it? So what will become of bx dot? So should I start by rewriting b first?
Yeah.
Okay, so b would be there, and s times what? Absolutely, s times x of s. So we're done with two of the terms. So one of you guys sitting in the back row. So would you like to take a shot at the last term that is kx? What will happen to it? Absolutely. So it's simply k, which is the stiffness of the spring, times x of s. So we're done with three items. The last one, what will happen to f? F is a function of time when it's in differential equation form. How would it transform to Laplace domain? There's no differentiation, no integration. The only thing we know is it's a function of time. So it will become f of s. Okay, so we have everything that we need to form the transfer function model. So what the ratio is x of s over f of s. To make it easier to write, it makes sense to factor x of s out from the left side of the equation. So let's do that. So let's factor x of s out. So x of s multiplied by m s squared plus b times s plus k equals f of s. And we are now ready to form the ratio. The ratio, which we call g1 of s, is equal to, okay, tell me what needs to go to the numerator and what should go to the denominator. So what is that ratio? So numerator is just 1. Denominator?
The entire quadratic. The ms squared plus bs plus good.
So that's the transfer function. So if you look closely, the denominator of the transfer function is very similar to what? It's very similar to here, to the differential equation. So essentially, the denominator of the transfer function carries a lot of information. So the denominator of the transfer function, as we go forward and we'll see, carries a lot of information about how the system behaves. How the system behaves is embedded into the denominator of this transfer function. Any questions on how we got to this ratio? Yes, sir.
Are we assuming that f of s is 1 then, or how do we get the...
To 1? Oh, how do we? Very good question. The way we got to 1 is this. We know the ratio of is x of s over f of s. Now, in order to get to that ratio, what I need to do is to take both sides of this equation and divide it by f of s, because I'm after that ratio. So let's do that. So if you divide this side by f of s, and also divide this side by f of s to keep the equation, then this side, this becomes 1. This is the ratio that I'm after. So in order to get to this ratio, this is 1, I need to take this and bring it to the denominator. So this ratio is xs over fs, which will be equal to that. Very good question, thank you. Anything else? Okay, now it's your turn. I'm not going to give you the solution. You need to solve it. Solve this, so turn this differential equation, x double dot plus 2 zeta omega n x dot plus omega n squared x equals, what should we call it? It's equal to f over m, which also we call lowercase f. So find the transfer function g2 of s between x of s and f of s, the capital F of s, which is the applied force. So find a transfer function between displacement as output and force as input. I'll give you 30 seconds. Okay, so what should go in the numerator and what in the denominator? Yes. You can have 1, and then what will you do with your m? M will go to the denominator? Okay. So it, uh, give me, what is going on with this guy? But is it okay if I write 1 over m here? Would have the same effect as m being in the denominator. I want to do that so we can see the similarity of the denominator with the differential equation. So what would be um, okay, so if that is the case, then the denominator becomes s to power 2 plus 2 zeta omega ns plus omega n squared. Can you see that? Now, again, the denominator of the transfer function looks exactly like the left-hand side of the differential equation. Anytime you had double dot, now you have s squared. Anytime you had, anywhere you had dot, you have s. And when it was power no derivative, then you don't have s. So it's very similar to what you had in the differential equation. So we have now dealt with 2 second-order differential equations and turned them into transfer functions. Okay, here's now the reason we did that is to prepare for this system. So in this system, you already have the 2 second-order differential equations. You just need to flip back a few pages and find those, find the 2 differential equations. What we are trying to establish here is a transfer function between input u, which is the road roughness, and displacement of the first mass. Displacement of the first mass, also displacement of the second mass, also the ratio between displacement of the first mass and the second mass. So this third transfer function, this here, this third, so this first transfer function tells you as the road profile changes and the road roughness comes as an input, what is the displacement of the second mass, this mass. The second transfer function relates the displacement or the road roughness to displacements of mass 1, and the last one relates the displacement of 2 masses to each other. And that is a perfect example to show you the versatility and the benefits of using transfer function, because from the exact same differential equations, you can establish different models. It would be hard to see between 2 second-order differential equations the relationship between Q1 and Q2, or the relationship between U and Q1, or the relationship between Q1 and Q2 separate from the rest of the variables. And so that's one of the main benefits of converting your differential equation into a transfer function, because you isolate relationships. You can extract relationships and don't pay attention to the rest of the dynamics of the system. So let's find the solution, and I'll explain more how each of them works. So if you don't have your notes, I can bring the differential equations. It was on one of these previous slides. Is this here? Not yet. Here. So what I have as equation 1 and 2 are the two differential equations for this system. So the first differential equation is m1 q1 double dot plus k1 plus k2 times q1. Is it equal to k2 times q2? Let's go back. It's equal to k2 q2 k2 q2. That was the first differential equation. The second differential equation is m2 q2 double dot plus b q2 dot plus k2 plus k3 q2 is equal to k2 q1 plus k3 u. Let me double check one more time. K2 q1 k3 u. I think we got it. So these are the two differential equations. So what are we after? We are after three separate transfer functions. The first transfer function that we are trying to find is this one. Let's call this g1 of s. In this transfer function, the input is u, the displacement of the road roughness, and the output is displacement of the second mass, q2. In the second differential equation, the input is the same, it's u, but the output is the displacement of the first mass. So let's call this g2 of s. And the last transfer function, the input is displacement of the second mass, and the output is displacement of the first mass. We are going to call this g3. And once we have these, we can answer the last question. What is the order of each of these systems? So what is the first step? What should we do? Let me ask you here. So we take both differential equations and take them to Laplace. What would come out of the first equation while we add it? So what will m1 q1 double dot become? becomes m1 what? Multiplied by what? S squared q1 capital of S. So m1 S squared, again the assumption is all initial conditions are equal to 0, plus k1 plus k2 multiplied by what? Capital Q1 of S equals to K2 multiplied by, exactly, so that's one equation we can get. Let's go to the second equation, which will become m2 S squared Q2 of S plus B multiplied by what? Bs times Q2 of S plus K2 plus K3 times Q2 of S equals K2 Q1 of S plus K3 U of S. We turned everything into Laplace. Okay, let's call this equation 1 and this equation 2. Now, when you look closely at equation 1, what transfer function can you find from equation 1? Yes, you see Q1 and Q2 present in there. So you can form a G3, which was what? G3 was Q1 over Q2. So you can immediately take 1 and form it into G3, which was Q1 over Q2. Was it Q1 over Q2? Yes. Okay, so do we know the answer immediately or do we have to do anything to it? So what goes in the numerator and what goes in the denominator? Try this one more time. So numerator is what is multiplied by Q2 already, right? Which is? Exactly. Denominator? Denominator is what is multiplied by Q1 in equation 1. What is multiplied by Q1? It is m1 S squared plus K1 plus K2. Yes or no? What mistake did I make? Or did we make? I was following. Anything? Did you find something else? If you did, let me know and we'll correct. Anything? No? Is it okay? Okay, so we got our last transfer function. So we now have a model. So this model shows as as mass 2 moves, if mass 2 was the input, the motion of mass 2 was the input, how much mass 1 would move as a result? Output is always on the top, input at the bottom. So this answers this question. So this transfer function answers this question. As mass 2 moves, how will mass 1 will will move. Will it follow? Would it go in the reverse direction? How long does it take? So all of those questions can be answered by this model, this transfer function. What is the order of this system? It's a second order system. Now, if you compare the denominator of this transfer function to the denominator of this transfer function, g1 of s, what do you see? Compare this, g1 of s, where you have ms squared plus bs plus k, to the denominator of g3. What do you see? Or more importantly, what is it that you don't see as in the denominator of this transfer function? There is no bs, which means there is no damping. So as mass 2 moves, mass 1 would move, but there is nothing to take energy away from that motion. And that's not necessarily a good thing when you talk about suspension. So keep that in mind. Okay, so we found one of the three answers that we wanted to find. If you look at the second equation, what we call equation number 2 here, you see Q2, you see Q1, and you see U. So there are three variables involved here. So we need to drop one or get rid of one if we want to find a relationship between U and Q1 or U and Q2. So let's go ahead and rewrite this equation number 2 by factoring Q2 out first. So if we factor Q2 out, so Q2S, if we factor it out, we'll have M2S2 plus B times S plus K2 plus K3. This is equal to K2 Q1 of S plus K3 U of S. If I want to get rid of Q1, how can I do it? Let's call this equation, by the way, equation number 3. The equation for G3, let's call it equation number 3. How can I take advantage of equation number 3 to get rid of Q1 in this last equation? According to equation number 3, what is Q1 equal to? So let me write it here. According to equation 3, Q1 is equal to Q1 is equal to Q2 multiplied by G3. I'm not going to repeat that ratio, but that ratio is K2 divided by M1S squared plus K1 plus K2. Do you agree? Okay, now I can take advantage of this and get rid of Q1 in equation number 4. So we are going to call this equation 4. Why are we doing that? Because I'm trying to establish a relationship between input U and output Q2. So I need to get rid of Q1 in that equation, so everything is in terms of Q2. So let's rewrite equation 4. So equation 4 will turn into, so still we have Q2 times M2S squared plus BS plus K2 plus K3. This is equal to K2 times Q1. Now for Q1, we are going to write it as Q2 times G3, which is what? Which is K2 divided by M1S squared plus K1 plus K2. This is K2 times Q1 plus K3 times U of S. It seems complicated, but we are there. We now have one equation that has both Q2 and U in it. So we can establish the ratio between Q2 as output and U as input. Okay, so let's factor all Q. So we have Q2 multiplied by M2 S squared plus PS plus K2 plus K3. That's from one side. From the other side, if I take the other term into the other side, I will have minus K2 to power 2 M1 S squared plus K1 plus K2. This is all equals K3 times U. So what did I do? Let's go back. I factored all the Q2 terms. Now, so I took the term from the right-hand side to the left-hand side and changed the sign. So I will have, so this portion, the third term, will turn into K2 times K2, which is K2 squared, over M1 S squared plus K1 plus K2, with a negative sign on the other side, which is what we have. Okay, we're getting very close. So we can take one more step if you want to and make M1 S squared plus K1 plus K2 the common denominator. So it's easier to manipulate. So what we can do is we can write Q2 multiplied by, so it would be, if we make M1 S squared plus K1 plus K2, the common denominator, we'll have M1 S squared plus K1 plus K2 multiplied by M2 S squared plus BS plus K1 plus K3 minus K2 squared is equal to K3 times U. This should be K2, right? So this is K2 plus K3, so this should be K. Let me see if I can erase and change that to K2. So this is K2 plus K3 minus K2 squared, and the parentheses is closed. Right. So the parentheses should be closed after this. Okay. Are we ready to form? Any questions so far? Let me know if I missed a step or something is not quite clear what I did or you disagree. Okay. The next step is to create Q2 of S over U of S. That's the transfer function. What did we call this transfer function? Q2 over, we called it G1 of S. So this is G1 of S. Okay. So what goes in the numerator? K3 multiplied by the denominator here. Okay, so it would be K3 multiplied by M1 S squared plus K1 plus K2. This is what is multiplied by U. So what is multiplied by Q2 is longer M1 S squared plus K1 plus K2, close parentheses, open parentheses, M2 S squared plus KBS plus K2 plus K3 minus K2 squared. So what is the order of this system? Where do we look to determine the order? The denominator. Now, what is the highest power of S in that denominator? Unless you multiply both of these parentheses. If you do that, then the highest power of S becomes 4. So this is a fourth order system. This is a fourth order system. So we have one last transfer function to find. What is that transfer function? It is the transfer function between Q1 of S and U of S. So we have to do a lot more work again, right? The answer is yes, unless we have already solved that problem. And I think we have already solved that problem. I'll give you 30 seconds to tell me why we have already solved that problem so we don't have to do a lot more work again. How have we solved? Yes, sir. Which means what? Which means U of S, yeah? So you just take those two, multiply. Exactly. So we have already solved that. So that's another benefit of dealing with transfer functions. They follow algebra. So instead of dealing with differentiation and integration in differential equation domain, you just deal with algebra, multiplication, division, additions, so on and so on. Okay, so what we just said was that Q1 over U is equal to Q2 over U multiplied by Q1 over Q2. So if you have both of these two ratios, you can just multiply them by each other and get to where you want to be. So the first ratio is G1, which is what we just found. Do we have the second ratio, Q1 over Q2? Q1 over Q2, yes, we have it, and we called it G3. So that's G3. So if you take G1 of S, which is that ratio that we have here, and multiply it by G3, then you have what we call G2. So this is, we gave the name of G2 to this transfer function. So this is equal to G2. And what was G3? Let's take a look at it. G3 was K2 over M1 S squared plus K1 plus K2. So another good news is multiplying by G3 will simplify G1. So let me rewrite. So G1 is right here, so I don't have to rewrite it. So it's G1 multiplied by G3. What was G3? G3 was K2 divided by, so K2 divided by M1 S squared plus K1 plus K2. So you should be able to see the good news. If you multiply this ratio by this big ratio here, it will get rid of m1 s squared plus k1 times k2 of the numerator. Basically, it will simplify that ratio. So the end result would be equal to, so our numerator will simplify. It becomes k2 times k3. And the denominator will simply repeat. So it is, open parentheses, m1 s squared plus k1 plus k2, close parentheses, open parentheses, m2 s squared plus bs plus k2 plus k3 minus k2 squared. Questions? Should we go to the... So the additional example document that I shared with you has many more examples. Please take advantage of it. We'll start today a third way of modeling, which will be the last way of modeling that we will discuss in this course. So far we've talked about two approaches of modeling differential equations, and we'll stop at, once we get to the differential equations, that's the end of it. And we try to put them into a standard form and learn about the behavior of the system just by looking at the standard form of the differential equations. We talked about first order, second order, and we showed examples of both. We also talked about the transfer function as the second approach of modeling, and it was based on differential equations. It was based on taking differential equations from the time domain into Laplace domain, and you saw so far some of the benefits. Even though it sometimes involves a lot of algebra, the benefit is you can arrive at various relationships and see those easier than seeing them from the differential equation. So that example that we just discussed was a very good example. Now, the last approach in modeling called a state space modeling. You remember the concept of a state variable? It starts from the concept of state variables. And sometimes there are single state variables if we are dealing with a first order system. Sometimes it's a vector of a state variable. So it's called a state vector if you have more than one state variable if you're dealing with higher order systems. The concept of state space is to limit our highest derivative to 1. So the concept is we know a whole lot about first order systems. It would be very nice if we can turn any higher order system and turn it to a bunch of first order differential equations. That's the whole concept or the main concept of state space models. So this, what I have here in the middle, is a state space model. Look at it for a second. It basically, it has two portions, by the way, instead of being a single portion like a differential equation or a transfer function model. A state space model by default is a two-portion model. Now the first portion basically tells you how derivative of a state vector, x is a state variable or state vector, how derivative of a state vector is a function of a state vector itself and the input. Look at it again. It basically tells you how x dot is a function of x and u. Isn't that very similar to the first order differential equations we had? We had exact same shape, if not arranged exactly like it in first order differential equations. Essentially, it said how state variable change with time, and that's exactly that form. Now, the second part of the transfer function tells you what is your output. Y is a variable that is reserved for output. What is the output, and how output is a function, again, of a state variable, and potentially, this is very rare that the output is directly function of output, but if we want to keep it general, if there was a case that output was directly a function of input without any dynamics involved, that would be the fourth portion of this state space model. That's the essence of it. So let's try to start from these differential equations and turn them into state space form. So let's start with this first differential equation. Let me add a page here. So the differential equation is this: a times dx over dt plus b times x is equal to u. For now, let's forget about the disturbance. So that's the form. It's a first order differential equation, and our goal is to take it into this form, the form that has x dot as ax plus bu and y is equal to cx plus du. In other words, I want to know what a, b, c, and d are. Once I have that, I have my state space model. That's the meaning of a state space model. State space model. Don't, of course, not to be mistaken with steady state. This is state space. Okay, so it's fairly straightforward. What we need to do simply is to keep x dot on one side and push everything to the other side. So if you rewrite this equation, so x dot is on one side, you will have minus b over ax plus 1 over a u. So what is the capital A for us? Capital A is this guy, and capital B is this guy. You need to really focus. I'm going to have a challenge question for you. What is the output of this system? Output of this system? Let's review. We said output is one or more than one of the state variables. So what is the state variable here? X. The only variable that is being differentiated is x. So x is the only The one and only state variable. So what is the only choice of output that we have? X. It's so simple that it's challenging because of the simplicity. So y output simply is equal to x. So what is C for us? C is 1. Look at the standard form of state space. The standard form says y is equal to c times x plus d times u. So what is c equal to? 1. And what is d equal to? Did you say 0? You're absolutely correct. Because y is equal to x and there is no u in it, which means d is equal to 0. So d is 0. That was one example. So the only thing we did with this first order differential equation was to rewrite it so it resembles the form of a state space model. And by rewriting it, we found A, capital B, capital C, and capital D. So capital A is minus lowercase b divided by lowercase a. Capital B is 1 over lowercase a. Capital C is 1. And capital D is equal to 0. And remember, for 99.99% of cases, D is going to stay 0. For almost all cases in this course, D is going to stay 0, which essentially says input doesn't directly affect the output. The input does affect the output, but through the dynamics of the system, through the first part of the state space model. See, the first part shows any dynamics for the system. Whenever we have dot, when we have time derivative, that's an indication of dynamics. That's an indication of a delay between input and output. If we had a non-zero D here, what we are basically saying is that input immediately affects the output without any dynamics involved. That's a static system. And because we are dealing with dynamic systems, for almost all cases, D is equal to 0. It's a very rare exception when D is non-zero. Okay? So this was a very trivial question. Because of that, probably it was a bit challenging. So let's go ahead and look at a second order differential equation. Okay, so our second, let's add another. So our second example is this. I want to make a change of variable so we wouldn't mix things up. So bear with me for a second. We are still talking about a mass damper spring system. But for my displacement, I'm not going to use x because I want to use x to represent my state variable. Are you following me? Okay, so what I'm going to do is I'm going to use another variable for displacement. So displacement I'm going to show it with variable p, and velocity would be p dot. And of course, acceleration would be p double dot. So acceleration so what I will have as a result is m p double dot plus b p dot, not q, p, plus k p is equal to f of t. And I'm not going to write t anymore. I'm just trying to say that all of these variables are functions of t. So p, of course, is a function of t, p dot is a function of t, and p double dot are functions of time. Okay, what is our goal? What are we trying to do? We're trying to take this second order differential equation and turn it into a state space model. Okay, so let's stay here for a second. What is the input to the system? Okay, so U is going to be F. So that's the input to the system. So that's our input. What is the input or possible output? I'm sorry, what is the output or possibly outputs of this system? So position and velocity, or a combination of them. So keeping them both or keeping them one. So let's choose one because it's going to help if we choose one. So let's assume the output that we are interested in is P. I only need to know position, and I'll be happy if I know the position. Okay, state variables. What are the state variables here? We have two of them because we are dealing with a second order system. So state variables are, what are the state variables? Position and velocity, P and P dot. Okay, and the form of the state space that we are after is this. We want x dot as a function of x and u, and we want output as a function of x and u. That's if we get to these two lines of equations, we have our state space model. That's what we need to do. Okay, so let's start with x dot. What is x dot? Let's figure that out first. What is x dot? What is x dot equal to? We know what x is. So what is x dot? Of x, which is what? Which is going to be p dot and? Exactly. So that's the meaning of x dot for this problem. Do you agree that this is x dot? Okay. Now what I need to do is to relate x dot to x and u. How is x dot a function of x and u? How is x dot a function of x and u? So let's start with the first element of x dot. X dot, by the way, has two elements. It's a column vector, so it has two elements. So we need to know how p dot, the first member of x dot, is a function of x, and how p double dot is a function of x. Knowing x also has two members. It has p and p dot in it. Okay, so to help us write things easier, I'm going to call this x dot 1 and call this x dot 2 to refer that the first one is in row 1 and the second one is in row 2 of that column vector. That's the meaning of that. Okay? The same way we can call the first row of x, x1, and the second row of x, x2. Okay, so here's my question. What is x1 dot equal to? It is equal to p dot, don't you agree? Okay. Now, if I want to write this in terms of members of x, do you see any relationship to members of x? How x1 dot is related to x1 or x2? It's equal to x2, isn't it? Is that what you meant? It is equal to x2. Can you see that, everybody? Basically, the first member of vector x dot is equal to second member of vector x. Do you see that? Okay. Now, so we answered one half of the first part of the state space model. Let's go to x2 dot. So x2 dot is p double dot. How is that related to x1, x2, or maybe u? How is p double dot a function of p dot, and u, which is f. Yes? Did you know the answer? Or you want to offer a suggestion?
Related through force equals mass times acceleration. If p double dot's acceleration.
If p double dot is acceleration, that is equal to sum of all forces divided by mass. Absolutely, that's the Newton's second law. But what is this equation? This equation at the top, isn't that Newton's second law? So maybe we can use this equation at the top to relate p double dot to p and p dot, which are x and x1 and x2. Can we do that? Let's at least give it a try. Maybe we will find something. So p double dot, according to this equation, equation 1 is equal to 1 over m f of t minus b p dot minus kp. If I want to use the language that we just developed, what is f of t? What is f of t? F of t is u, input. So u minus, what is p dot? P dot is what? P dot is, I want to call it, let me call it and then ask you if you agree. It's x2. This is the second member of x. Isn't p dot the second member of x? How about p? What is p? What is p? Isn't it first member of x? So it's x1. So essentially, we have already figured out the first portion of the state space model. Isn't the first portion of a state space model what x dot is in terms of x and u? Let me rewrite. Let me summarize what we have already. We have this, that x1 dot is equal to x2. That's what we already found. And we have x2 dot as 1 over m u minus kx1 minus bx2. That is essentially the first part of the state space model. But it's not as clean as it can be. It's a little bit messy. It's two equations. It would have been nice if we can combine them into one. Can we combine them into one? Do you guys think? Because it's difficult for me to see what A is. See, I want one A and one B, capital A and capital B. It would have been nice if I can combine them so I can see what A is and what B is. Do you guys have any suggestions on how to combine them?
Check the integral, the second equation, since x dot 1 is equal to x2.
Oh, you're saying combine them into one equation because that's how they're related. Yeah, that's how they related. But I would deviate from the format I want. Let me help a little bit here. So what I mean is, it would be nice if I can form a vector of x and call it x dot and relate it to the vector of x, which I already have defined. So my question is, how is x dot related to x and u in one equation? I'm not trying to develop a new equation. I'm trying to combine the two into one writing. That's it. That's what I'm after. Okay? So what if, see, what is x1 dot equal to? x1 dot, which is the first member of this guy, is equal to the second member of this. If I write 0 here and 1 here, that is exactly what I'm saying. By writing 0 there and 1 there. And also 0 here because there is no u involved. By the way, what is this called, this structure? It's a matrix. So it's a matrix. So this is a vector. It has only a column. It's a column vector. But this is a 2 by 2 matrix. Okay. So with that notation in mind, what should I write here as the second row to capture this equation? So what is multiplied by x1? Minus k over m, isn't it? So x1 is multiplied by minus k over m. Can you see that? So is it okay if I write minus, that's going to be a challenge. Minus, I'm going to write it here and then move it. Minus k over m here. That's what is, it's multiplied by x1. And what is multiplied by x2? Did you say minus b divided by m? And what is multiplied by u?
1 over m.
Absolutely. So that's it. So I'm going to see if I can move them into place. So I have what I have been able to do is to create the first part of the state space model using matrix language. So do we know what our A is now? And what our B is? A is what? A is a 2 by 2 matrix. 0, 1 minus k over m minus b over m. B is also a vector. It's a 2 by 1 vector. 0, 1 over m. So what is left? To look at the second part of the state space model. So what is y? Y is equal to what? Y is equal to, we decided it's equal to p. What is p in terms of members of x vector? Look here. Is it the first member of x or second member of x? So it's equal to x1. If I want to use the exact same language that I used here, y therefore would be equal to what should go in here to reflect that y is equal to x1 and not x2? One and 0. How about this scenario? If we wanted y to be equal to x2, which is the velocity, y would have been, instead of 1, 0, would have been 0, 1 times x plus 0, u. So let's spend a few minutes and talk a little bit about what we call linear algebra, which is partly dealing with matrices and vectors. Okay, so let's say I have a matrix A, B, C, D. And I want to add it to another matrix that is E, F, G, H. First of all, you can only add matrices that are the same exact dimension. What is the dimension of each of these two matrices? 2 by 2. How do you call it? Number of rows first, number of columns second. So this is 2 by 2 because it has 2 rows, 2 columns. So each of them are a 2 by 2 matrix. This is number of rows. This is number of columns. Number of rows, number of columns. So each of them is a 2 by 2. So what is the resulting matrix? It is going to be also a 2 by 2. So what is row 1, column 1 element? It's A plus E, absolutely. Row 1, column 2? Is going to be B plus F. Row 2, column 1 is C plus G. And row 2, column 2 is D plus H. Here you go. So that's addition of two equal dimension matrices. Now let's talk about multiplication. We talked about what matrices can be added to each other. In multiplications, when you multiply two matrices, let's say you are trying to multiply A by B, and A is of M by N, the other matrix first dimension has to match the second dimension of the first matrix. So this has to be N by P. See, these two should be the same. The inner index of the two should be the same. So that means, for example, if this is our first matrix, A by B, what is the dimension of this matrix? Dimension? It's 1 by 2. It can be only multiplied by a matrix that has, this has 2 columns. The second matrix has to have 2 rows. The number of columns could be anything, but it has to have 2 rows. So let's do this. Let's say we're going to multiply this by a matrix that has 2 rows by 3, but 3 columns. So this time let's use numbers. So 1, 2, 2, 5, minus 2, 7. So this is 2 by 3. Now, what is the dimension of the resulting matrix? So we are multiplying a 1 by 2 by a 2 by 3. What is the dimension of the resulting matrix? The dimension of the resulting matrix would come from the outer 2 indices. So the resulting matrix would be M by P. The resulting matrix would be M by P. So in this case, would be what by what? It would be 1 by 3, which means it's a column vector, has 1, or the other way. No, it has 1 row, 3 columns. So it's a row vector. 1 row, 3 columns. So 1 row, 3 columns. So what is column 1? How do we get to column 1? So it's going to be 1 by 3. That's the dimension. So I need column 1. How do we find? Yeah, so you take the row and multiply it by the column. So the first element would be A plus 2B. Do you see that? A times 2B. That's column 1. That's the content of column 1. Now, what is column 2? You need to tell me. It would be 2A plus 5B. Absolutely. So it would be 2A plus 5B. And we leave a space to indicate that we are now in the second column. And the last one would be minus 2A plus 7B. Is it 1 by 3, the dimension of this? So it's 1 row, 3 columns. Okay, The next concept that you need, probably a quick refresher, is the concept of determinant of a matrix. Square matrices have determinant. Square matrices have determinant. So for example, if matrix A is A, B, C, and D, determinant of A is a number. It's no longer a matrix, it's a number. So determinant of A is A times D minus B times C. So the two diagonal elements are multiplied, the two off-diagonal elements are multiplied, and they're subtracted from each other. So that's A D times B times C in this case. The next thing is A transpose. What is A transpose? A transpose means row and columns would switch. So this element, A, lowercase a, is at what row and what column? A is at row 1, column 1. So if you change row and column of that element, it's still at row 1, column 1. So in the transpose form, it still is at, it's right here. Now, in the original matrix, what is row and column of B? It's row 1, column 2. So in the transpose, it becomes row 2, column 1. So it means B will go here. Now, in the original matrix, C is what row, what column? C is row 2, column 1. So in the transpose, goes to row 1, column 2. So it basically comes here. Now, D is what? In the original matrix, D is column 2, row 2, column 2. So when you switch then, it becomes still row 2, column 2. So it stays exactly where it is. So that's the transpose of a matrix. What else do we need to review? Maybe the next thing to review is inverse of a matrix. By the way, if you multiply A, so let's say A is A, B, C, D, and it's in a way that determinant of A is non-zero. So it has to be the case. The determinant has to be non-zero. We don't know A, B, C, and D what numbers they are, but it has to be a combination of numbers that A times D is not equal to C times B. If that is the case, then the determinant would be 0. Now, if that is not the case, if the determinant is not equal to 0, if we take inverse of A, which we show by A to power minus 1, and multiply it by A, the result is what? The result is equal to a special matrix, which we call the identity matrix. The identity matrix. Now, the identity matrix is a special matrix where if you're dealing with 2 by 2 matrices, it's going to be 1, 0, 0, 1. So all the diagonal elements are 1, and all the off-diagonal elements are equal to 0. That's the definition of the identity matrix. Okay, so what is inverse of it? So I expect you to know how to find inverse of 2 by 2 matrices in this course. So how do you find inverse of this example? So inverse of A, so 2 by 2 has a special procedure. So again, inverse is a matrix. In the denominator, it has determinant of A, and that's why determinant of A has to be non-zero, because in finding an inverse, we divide by the determinant. Then in the numerator, so because we are trying to find row 1 and column 1, you eliminate row 1 and column 1, and what is left, you write. So it's D. So for row 2, column 2, you eliminate, for row 1, column 2, you eliminate row 1 and column 2. So what is left will go here. And this will have a negative sign. So this also will have a negative sign. So if you eliminate column 1, row 2, what is left is B with a negative sign, and the last one is A. And this matrix needs to be transposed. So what is left is, if you apply the transpose, you still have the determinant at the denominator. This is D. This is minus B minus C A. This is A inverse. Now, how do we know if this is really A inverse? The way to know is to multiply it by A. If you multiply it by A and the result is the identity matrix, we have found the right inverse. If not, something is wrong here. Because we are at the time, I'm going to stop here. But please look at this and work on it to make sure